Okay, for what we have concerning functions and operations, we're looking at the sum, difference, product, and quotient functions. And we have with f plus g of x, okay, that is equal to f of x plus g of x. Okay, and this is for two functions, f of x and g of x. For the difference of functions, okay, we have f minus g of x is equal to f of x minus g of x. For the product functions, if you have the product function f times g of x, we have this equal to f of x times g of x. And for f over g of x, we have f of x over g of x. Now, out of these four operational functions, okay, the sum, difference, and product functions will have the exact same domain, which will be formed by combining the restrictions, if there are any, of f of x and g of x. Now, for what we have in the quotient function, f over g of x could possibly have a different domain. All right, and let's say that as an example, okay, if we have given f of x is equal to 3x squared plus 2, and g of x is equal to 4x, okay, let's see what we have for the following functions as well as the domain. Okay, and let's say that if we have, for instance, okay, so we have with our four operational functions, now we have with f plus g of x, so you have f of x plus g of x. So if I add these functions together, so I have 3x squared plus 2. For g of x, I have plus 4x. And if I add the terms together, and it really doesn't matter what order you place them, once you take out, say, the parentheses, and I just grouped to identify, you have f of x here, g of x represented by the quantity of 4x. And if I join together, we have for the outcome, we have 3x squared. You can say plus 2 plus 4x, but if I rearrange and put in descending degree order, so I'm going to have 3x squared plus 4x plus 2. Okay. Now, for the difference of functions, okay, so I have 3x squared plus 2 minus 4x. And for 3x squared plus 2, we're going to take away g of x, which we have at 4x. And if I rearrange the terms in descending degree order, so we have 3x squared minus 4x plus 2. Okay. Now, and what we have for the product functions, now we have for f times g of x. So breaking this up, we have f of x times g of x. For f of x times g of x, we have 3x squared plus 2 quantity times the quantity of 4x, and we have with multiplying, so you have 3x squared times 4x, so this will come out to 12x cubed, and 2 times 4x, so this is going to end up at 8x. And as for what we have in the case of the quotient function, we have the quotient of f of x to g of x. F of x we have at 3x squared plus 2, and we have divided by g of x, which we have at 4x, and so we have 3x squared plus 2 all over 4x. Now again, we have with f of x equal to 3x squared plus 2, and g of x equal to 4x. Okay, if you notice, we don't have a fraction, and we don't have an even root radical, and we have for f of x, okay, we have no restrictions. And for g of x, we have just 4x, so we also have no restrictions. Also for the domain of g of x, we're going to have the set of all real numbers. Okay, and symbolically we have, again, for the interval notation, we have going from negative to positive infinity. And since there are no restrictions for either of these two functions. We're not going to have any restrictions for the sum, difference, and product functions. And again, just as stated earlier. Okay, again, so we have for the sum, difference, and product functions, they're going to have the exact same domain, which will be formed by combining the restrictions, if any, of f of x and g of x. Okay, so we have for the sum, difference, and product functions. Okay, again, we have for these as well. So again, we have for the sum, difference, and product functions, we're not going to have any restrictions. And so it's going to turn out that for these three operations, okay, we're going to have the domain to be the set of all real numbers. Now, it is with the quotient function that we can have this to be pretty much the odd man out. Okay, and this is exactly what is going to arise in this particular situation. Okay, so while the sum, difference, and product functions will not have any restrictions on the variable x, now again we have for the quotient function, again, we had earlier determined that f over g of x is equal to 3x squared plus 2 over 4x. So just going back, okay, this time we're going to have a restriction, and that is since we have a fraction, fractions will not allow zero denominators. So in this case, we have 4x cannot be equal to 0. So we have x cannot be equal to 0. And so for what we're going to have in consequence, okay, is that while the sum, difference, and product functions will have the exact same domain, that is the set of all real numbers, the quotient can have a distinct domain, and this will turn out to be the case. All right, so we have for the domain of the quotient function, okay, we have all values of x excluding 0 and utilizing interval notation. So we're going from negative infinity approaching but not including 0. So you have from negative infinity to 0 in parentheses. That means we are leaving out 0, so you have values of x less than 0. And then for those values of x greater than 0, we have, again, another open interval. So if I have f of x is equal to, and we'll say that we have x plus 1 over x plus 2, and we have for g of x, I'll say that I have x minus 5 over x plus 9. Okay. Now, for f of x and g of x, now for f of x, okay, now you can have a 0 numerator as long as you do not have a 0 denominator. Now for this rational expression, x plus 2 cannot be 0. So we have that x cannot be equal to negative 2. Now for g of x, okay, again, we have another rational expression. Now x plus 9 cannot be 0. So we have that x cannot be equal to negative 9. Now, if I apply to what I have for the sum, difference, and product functions, okay. Again, in terms of being able to work with the sum, difference, and product functions, first of all, we have with the sum, difference, and product functions. Okay, so we have with all of these. Okay, so we have on the one hand, Okay, we have x cannot be equal to -2. And also x cannot be at -9. And now for f of x, if I express the domain in interval terms, okay, so we're leaving out only -2. Again, we have parentheses throughout. And for g of x, if I express the domain in interval notation, so again, I'm going to be using parentheses, leaving out or indicating the omission of -9. Now in the case of what we have with the sum, difference, and product functions, now all of these are going to have the exact same domain. And if I put this set of domains, okay, in interval notation, notice that for all three of these operations, okay, now -9 is a smaller exclusion. So for what we're going to have in the domain, so we have going past -infinity approaching, but not including -9. And then we have next in line have going past -9 approaching but not including -2. And then we have going past -2 on out to infinity. So for the sum, difference, and product functions, all of these will have the exact same domain, and that is indicated symbolically in the interval notation where we have excluding -9, -2, and so we have this layout. Now for the quotient function, okay, now we still have to keep x such that both f of x and g of x will be defined in the real number system. So we're still leaving out -2 and -9. Now, for what we have in the case of f over g of x, and we're going to have in this expression, so I have for f over g of x, okay, so I have f of x over g of x. Again, just for what we have originally, f of x, we have x plus 1 over x plus 2. And for g of x, okay, so I have x minus 5 over x plus 9. Okay. And here we have a bit of a complex fraction. And again, dividing by a fraction will be the same as multiplying by the fraction's reciprocal. So we have x plus 1 over x plus 2. And we have times what's going to be x plus 9 all over x minus 5. And you can just leave the results in factored form. So I have the quantity of x plus 1 times the quantity of x plus 9. And we have all over the product of the quantities of x plus 2 and x minus 5. If you notice what is in the denominator position, so we have x plus 2, x cannot be -2. X plus 9 cannot be 0, so x cannot be at -9. And if you notice that upon taking the multiplication of the reciprocal of g of x, we have a newfound denominator where we have x minus 5 started out as a numerator in the fraction, but now it is in the denominator upon applying what we have for this quotient function. So not only can x not be -2 or -9, but also it cannot be equal to -5. So if I take what I have here, we're going to have for the domain of the quotient function, we have 3 exclusions. Okay, -9 is the smallest of the exclusions. So we have going past -infinity, approaching but not including -9. Then we have going past -9, approaching but not including -5. Now we have going past -5, approaching but not including -2. And then for the rest of the domain, we have those values of x that will be greater than -2.